Hi, so we're going to talk about our last transformations of functions. They're going to be vertical stretches and compressions. So a vertical stretch, and also we'll talk about horizontal stretches and compressions. So first, vertical stretches and compressions. A vertical stretch is when we pull it and it gets taller. A compression is when we push it down and it gets smaller. So here we have a graph. The blue function is our original function. A vertical stretch, 2 times f of x would make it taller. And on this red graph here, 0.5 times f of x makes it smaller. So here we've got our definition. G of x equals a times f of x. So if there's a constant value out in front of a function, if a is greater than 1, it's going to be a stretch. And if it's between 0 and 1, it will be compressed. Okay, so if for vertical stretch or compression, it's just a constant out in front of the original function. And it will either stretch it, like 2 to the x, or compress it, like 0.5 f of x. Okay, here we've got a function modeling a population of fruit flies. Okay, and maybe we want to stretch this by 2, vertically stretch this by 2. I have to say this is a graph from our textbook and they don't exactly match, so this isn't like a great example. But this point 0, 1 goes up to 0, 2, right? The input stays the same, the output doubles. Here, this is where this is a little bit off. This point isn't actually the same point on this graph. But if there was a point 3, the input would stay the same and the output would double. So it would go from 3 to 3, 6. This point 6, 2 is the same point on this graph. 6, 2 would go to the point 6, 4. Input stays the same, output doubles. 7, 0 stays at 7, 0 because 0 times 2 is 0. Okay, so this would be an example of how the graph would stretch if you had a vertical stretch by 2. The input stays the same, the output doubles. What if we had a table? Okay, so here's some input values for x and output values for f of x. And now we have a new function g of x they want us to make a table for. But our new function is 1/2 times f of x. Well, the input values stay the same, 2, 4, 6, 8. The output values we divide by 2. Right? We just multiply the output values by whatever this constant is in front of the function. If it was like 7, then we would just multiply all the output values by 7, right? Whatever this constant is, that's what we multiply our output values by to get the output values for our new function. Okay, so they're telling us this started, here we have a graph, and it's a transformation of this toolkit function, f of x equals x cubed. So how is it related to x cubed? Well, let's think of some recognizable points for x cubed. The origin, but they both cross the origin, and this still crosses the origin. Let's see, f2 cubed would normally be 8, but here it's only 2. Well, that's a clue. Okay, so it looks like the original function, f of 2 would be up here at 8, but it's down here, f of 2 is 2. So it seems like the function has been compressed by a factor of 1/4. Right? Would that make sense? Like f of 1 would be 1/4. Yeah, that looks like it could be 1/4. Okay, so looking at this point here was key. So looking at that gave us a clue. And yes, g of x is 1/4 times f of x, or 1/4 times x cubed. Okay, let's talk about horizontal stretches and compressions. Here, let's look at the equation first. If we have a horizontal stretch or compression, remember for a vertical stretch, the constant was outside of the function. Here, it's an input, right? If our constant is b, it's f of b times x. b is inside, the input is multiplied by multiplying times the input to our function. Okay, so if b is greater than 1, again, this is kind of opposite what you might think. If it's greater than 1, it will be compressed. And if it's less, between 0 and 1, it will be stretched by 1/b. Okay? And so here's our original function, x squared, blue, right? Our toolkit function. If we had 2x squared, it's going to be compressed. Okay, it's that green function. It gets taller. If it's less between 0 and 1, it is a horizontal stretch. It makes it wider. Okay? So let's look at what a graph would look like. Here we have our original population of fruit flies. Okay, so the y values are going to stay the same. It's going to go from 1 up to 3, down to 2, and then 0. 1 up to 3, down to 2, and then down to 0. But the x-axis is compressed by half. Okay, so 7 becomes 3.5. 6 becomes 3. So this was compressed by 2. What if we have a table? Okay, here we have input values 2, 4, 6, 8. Our output values 1, 3, 7, 11. And we want to make a new table for a function f of 1/2 x. So what's going to change? The output values are going to stay the same. Okay. But in order to get this output value of 1, our input's going to have to be twice as big, right? 1/2 times our new x has to equal 2. So we're actually going to multiply all these input values by 2 to get the same output values. And if we look at, these are just plots of the original functions, the original values in that table, and the new function, where we had to, the function, this new function was compressed, let's see. The new function was a horizontal stretch, right? It got wider because this function, this constant, was less between 0 and 1. Okay, and lastly, recognizing a horizontal compression on a graph. Okay, so relate g of x to f of x. So here's our original function f of x. Well, let's look. So this point, 6, 4, went over to 2, 4. So it looks like it got horizontally compressed by a factor of 3, right? So there we go, 3, right? Does that work? 4 divided, this became 4/3, right? But this key here is 6, 4 to 2, 4 was the easiest one to see, and that gave us our value of 3. And we knew it was going to be 3 and not 1/3 because it was a horizontal compression. Okay, so that's the last kind of transformation that we're going to talk about. In the next section, we'll put them all together.